What if the universe doesn't end? What if it just keeps going, stretching beyond anything you could imagine, beyond comprehension itself? Or maybe it does end, but not in the way you think. Maybe there's a boundary, an edge where reality itself stops being real. Tonight we're diving into one of the most profound questions humanity has ever asked. Where does space stop? It sounds simple, almost childish. The kind of thing you'd wonder about when you're 7 years old, lying in bed, staring at glow in the dark stars on your ceiling. But here's what makes it terrifying and beautiful all at once. The deeper scientists look into this question, the stranger the answers become. The universe doesn't play by the rules you expect. It doesn't need to make sense to your monkey brain that evolved to find berries and avoid tigers. And by the time we're done exploring this together, you might find yourself lying awake at night, staring at the ceiling, wondering if the universe is even stranger than we dare to imagine. Before we launch into the cosmic void, hit that like button if you're ready to have your mind bent into shapes that shouldn't exist in three-dimensional space, and subscribe if you want more of these deep dives into the terrifying majesty of the cosmos. Now, let's ask the question that keeps cosmologists up at night. Does space end? Here's something you need to understand right from the start. Space is not what you think it is. You probably imagine space as just emptiness, the dark stuff between stars, the void where astronauts float and planets orbit. A giant nothing where things happen to exist. But that's not what space is at all. Space is something. It's a physical thing, a structure, a fabric that can be bent, stretched, compressed and twisted. It has properties. It has energy. It can ripple like the surface of a pond when gravitational waves pass through it. Understanding what space actually is might be the first step toward understanding whether it ends. Let's rewind to the early 20th century. Back then, most physicists thought of space the way Newton did, as an absolute fixed stage where events played out. Imagine a giant cosmic theatre with a flat wooden floor. The floor doesn't move, doesn't change, doesn't care what happens on it. Actors come and go, the play unfolds, but the stage itself is permanent and unchanging. Time flows at the same rate for everyone everywhere. Space is just the three-dimensional grid that contains everything. Simple, intuitive, completely wrong. Then Einstein showed up and shattered that tidy little picture. His theory of general relativity revealed something profoundly weird. Space and time aren't separate things. They're woven together into a single four-dimensional fabric called space-time. And here's the part that breaks your brain if you really think about it. This fabric isn't passive, it's dynamic. It responds to the presence of mass and energy by warping and curving. Massive objects like stars and planets create dips and valleys in space-time. Other objects moving through that warped space follow curved paths, and we perceive that curvature as gravity. Think of it this way. You're not sitting in your chair because Earth's gravity is pulling you down like a magnet. You're sitting there because Earth's mass has bent the space-time around it into a well, and you're sliding into that curve. You're constantly falling toward the center of Earth, but the ground keeps getting in your way. That's gravity, not a force pulling you, but the shape of space-time itself guiding your motion. This completely changes how we think about space. It's not a container that things exist inside. It's more like a participant in every event that happens. When two black holes collide billions of light years away, space-time itself ripples, sending gravitational waves spreading outward at the speed of light. We've detected those waves here on Earth, felt the universe itself vibrating from events that happened before life existed on our planet. Space is alive in ways we're only beginning to understand, but it gets stranger. Even when space appears empty, when there's nothing visible, no stars, no gas, no dust, just darkness, it's still not actually empty. Thanks to quantum mechanics, we know that what looks like a perfect vacuum is actually seething with activity. At the smallest scales imaginable, scales where atoms look like galaxies, space is filled with quantum fields. These aren't things in space, they are space, or at least they're inseparable from it. Every particle that exists, every electron, every photon, every quark arises from its corresponding quantum field. Think of it like waves on an ocean. The ocean is the field, and waves are the particles. When a field gets excited enough, it creates a particle. When the particle disappears, the field is still there, waiting. Even in what we call a vacuum, these fields never stop fluctuating. They're constantly producing pairs of virtual particles that pop into existence and annihilate each other in fractions of a second. We can't see these virtual particles directly, but their effects are measurable. They influence how electrons behave around atomic nuclei. They contribute to the Casimir effect, where two metal plates in a vacuum are pushed together by the pressure of virtual particles. Space, even empty space, is not silent. It hums with quantum static. This quantum foam, as it's sometimes called, is one reason why physicists talk about vacuum energy. The energy of empty space itself, and this might be one of the most important numbers in cosmology, because it appears to be driving the accelerated expansion of the universe. We call it dark energy, though honestly we have no idea what it actually is. All we know is that empty space has energy, and that energy is pushing the universe apart faster and faster. The fabric of space isn't just dynamic, it's growing. So when we ask where space ends, we're not asking about some simple container. We're asking about a living, breathing quantum mechanical structure that bends around mass, ripples when disturbed, and expands for reasons we don't fully understand. We're asking if this structure has boundaries, if there's a place where space-time just stops, like the edge of a table where you could fall off into something else, or nothing at all. Now here's where things start to get uncomfortable. There's a difference between the universe and the observable universe, and that difference is critical to understanding whether space ends. The observable universe is everything we can possibly see, detect, or measure. It's defined by a horizon, a cosmic boundary beyond which light hasn't had time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light travels fast, but not infinitely fast, so there's a distance beyond which light from those regions simply hasn't reached Earth yet. That distance defines the edge of what we can observe. Picture yourself standing in the middle of an enormous foggy field at dawn. You can see a certain distance in every direction before the fog gets too thick. That circle of visibility is like the observable universe. But here's the critical question. Does the field end at the edge of your vision? Of course not. There's almost certainly more field beyond the fog, more grass, more sky, more reality extending past what you can see. You just can't observe it from where you're standing. The observable universe works the same way. We're limited by how far light has travelled since the beginning of time, but that doesn't mean space ends at that horizon. It might continue far beyond, possibly forever. The observable universe has a radius of about 46 billion light-years in every direction. Now you might be wondering, wait, if the universe is only 13.8 billion years old, how can light have travelled 46 billion light-years? Shouldn't it only be 13.8 billion light-years away? Here's the twist. Space itself has been expanding while that light was travelling toward us. Imagine an ant walking across a balloon while someone is inflating it. The ant is moving at a constant speed, but the surface beneath it is stretching. By the time the ant reaches the other side, it has travelled farther than its walking speed would suggest, because the surface itself grew during the journey. Light from the edge of the observable universe works the same way. It's been travelling for 13.8 billion years, but space has expanded so much during that time that those distant regions are now 46 billion light-years away. This creates a sphere around us, an observable bubble about 93 billion light-years across. Everything within that bubble is part of our observable universe. Every star, every galaxy, every quark and photon that could theoretically send us information. But here's what keeps cosmologists awake at night. We have no idea what's beyond that bubble. The universe outside our observable region could be completely different. It could have different physical laws, different constants, different types of matter we've never encountered. Or it could be exactly the same as what we see, just more galaxies, more stars, more planets, stretching on in endless repetition. Some cosmologists think the universe beyond our horizon is infinite, continuing forever in all directions without boundary or edge. If that's true, then somewhere out there, beyond the reach of any telescope we could ever build, there are other regions of space with other galaxies, and quite possibly other intelligent beings looking up at their own night sky, wondering the same things you're wondering right now. They'll never see us. We'll never see them. We're separated by distances so vast that light will never cross them before the universe ends. We're cosmological neighbours, existing in the same universe but forever isolated by the expansion of space itself. Other scientists think the universe might be finite but unbounded. That's a phrase that sounds like nonsense, but it makes sense when you think about the geometry of space. Imagine an ant walking on the surface of a sphere. The ant can walk forever in any direction without ever reaching an edge. The surface is finite, there's only so much area, but it has no boundary. You never fall off, you never hit a wall, you just keep walking, and eventually, if you go far enough, you come back to where you started. The universe could work the same way, curved back on itself in dimensions we can't visualize. You could travel in a straight line for long enough, and theoretically you'd end up back where you began. Space would be finite, with a specific volume, but you'd never find an edge because there isn't one. This is where geometry starts to matter. The shape of the universe depends on its overall density, and the distribution of matter and energy within it. Einstein's equations of general relativity allow for three basic possibilities. The universe could be flat, curved like a saddle, or curved like a sphere. Flat space goes on forever. Saddle-shaped space also goes on forever, just with weird geometry where parallel lines diverge. Spherical space curves back on itself and is finite. For decades, cosmologists have been trying to measure the curvature of the universe by looking at the cosmic microwave background radiation, the ancient light from when the universe was only 380,000 years old. This relic radiation fills all of space, and tiny variations in its temperature tell us about the geometry of the universe. The measurements are incredibly precise, and they all point to the same conclusion. The universe is flat, or at least so close to flat that we can't measure any curvature. That suggests space goes on forever. But there's a catch. We can only measure the curvature within our observable universe. If the universe is much larger than what we can see, it could have large-scale curvature that we simply can't detect. Imagine trying to measure the curvature of Earth by looking at a square metre of ground. It would seem perfectly flat, even though you're standing on a sphere. The universe could be the same way, curved on scales far larger than our observable bubble. So we're left with profound uncertainty. The universe beyond our horizon might go on forever, or it might curve back on itself. We might live in an infinite cosmos, or a finite one, and we might never know for sure because we're trapped inside our observable bubble, unable to see beyond the cosmic horizon. But let's take this deeper. Let's ask a more disturbing question. What if there are multiple kinds of edges? What if the universe ends in different ways depending on what we mean by end? There's the edge of the observable universe, which we've already discussed. That's not a real edge, it's just the limit of what we can see. But there could be other edges. For example, there might be an edge in time. The universe had a beginning, the Big Bang, roughly 13.8 billion years ago. Before that moment, time itself didn't exist, at least not in any way we understand. You can't ask what happened before the Big Bang because before is a time concept, and time began with the Big Bang. It's like asking what's north of the North Pole. The question doesn't make sense. The universe could also have an edge in the future. It might end in heat death, a slow fade into maximum entropy where all the stars burn out, all the black holes evaporate, and the universe becomes a cold, dark, lifeless void. Or it might end in a big rip, where the accelerating expansion of space tears apart galaxies, stars, planets, atoms, and eventually even subatomic particles. Or maybe it collapses back on itself in a big crunch, all of space-time contracting back to a singular point. Each of these scenarios represents an edge in time, a point where the universe as we know it ceases to exist. But there might also be edges in space itself, and these are the ones that really mess with your head. What if somewhere out there, far beyond our observable universe, space just stops? What if there's a boundary, a wall, a place where you can't go any farther because there's no more space to go into? This sounds absurd. How can space end? What would be on the other side? Nothing? How can there be nothing? Doesn't nothing have to be somewhere? These questions spiral into philosophical territory that physics can't easily answer. Here's one possibility that some physicists take seriously. The universe might have boundaries in extra dimensions. Our everyday experience involves 3 dimensions of space: up, down, left, right, forward, back, plus 1 dimension of time. But some theories, particularly string theory, suggest there might be additional spatial dimensions that are compactified, curled up so small that we can't perceive them. Imagine a tightrope walker. From far away, the tightrope looks like a 1-dimensional line, but up close it's actually a 3-dimensional cylinder with width and depth. An ant walking on the tightrope could move forward and backward along its length, but also around its circumference. Our universe could be like that. We move through 3 large dimensions, but there might be 6 or 7 tiny extra dimensions curled up at every point in space. These extra dimensions could have boundaries, edges where they end or connect to other structures we can't perceive. Another possibility involves the multiverse. What if our universe is not the only one? What if it's one bubble in an infinite foam of universes, each with its own space, time, and physical laws? In that scenario, our universe would have edges, boundaries where it meets other universes. But those boundaries wouldn't be edges in the traditional sense. You couldn't fly a spaceship to the edge and peer over into another cosmos. The boundaries would exist in a higher dimensional space that we can't access. Our universe would be finite, but embedded in something larger, something beyond our ability to observe or interact with. This brings us to one of the most unsettling ideas in modern physics, the holographic principle. This idea suggests that all the information contained in a volume of space can be encoded on the boundary of that space. Imagine a 3-dimensional object, a sphere, for example. The holographic principle says that everything happening inside the sphere, every particle, every interaction, every bit of information can be described by a 2-dimensional surface on the sphere's boundary. It's like how a hologram works. A 2-dimensional image contains all the information needed to reconstruct a 3-dimensional scene. The universe might work the same way. Reality as we experience it with depth and volume and 3-dimensional space might be a projection from a 2-dimensional boundary. If the holographic principle is correct, then the question of whether space ends becomes even stranger. Space as we perceive it might not be fundamental. It might be emergent, a kind of illusion created by information encoded elsewhere. The edge of space might not be a physical boundary, but an information boundary, a limit to how much data can be stored in a given region. This is deeply weird and profoundly counterintuitive, but it's taken seriously by physicists working on quantum gravity. So where does that leave us? We've explored what space actually is, a dynamic fabric of space-time that bends and stretches and hums with quantum energy. We've talked about the observable universe and the limits of what we can see. We've considered the possibility that space might be infinite or finite but unbounded, or bounded in ways we can't directly observe. We've touched on edges in time, edges in extra dimensions, and the deeply strange idea that space itself might be an emergent phenomenon. And through all of this, one thing becomes clear. The universe does not care about your intuition. It does not need to make sense to a species that evolved to throw rocks and pick fruit. The cosmos operates on scales and principles that our brains are simply not equipped to handle. We're like ants trying to understand calculus. We can sense that something profound is happening, but grasping it fully might be beyond our cognitive architecture. Here's something that might help or make things worse depending on your perspective. let's talk about what we can actually observe and measure. The cosmic microwave background radiation, that faint afterglow of the Big Bang, gives us a snapshot of the universe when it was only 380,000 years old. Before that moment, the universe was so hot and dense that it was opaque to light. Photons couldn't travel freely because they kept colliding with charged particles. But when the universe cooled enough for atoms to form, light suddenly had a clear path. The whole universe became transparent all at once, and that first light has been travelling through space ever since, stretched by cosmic expansion into microwave wavelengths. When we map the cosmic microwave background, we see tiny temperature fluctuations, differences of just a few millionths of a degree. These fluctuations are the seeds that grew into galaxies and galaxy clusters. They tell us about the density of matter in different regions of the early universe, and here's what they reveal. The universe is remarkably uniform. No matter which direction we look, the cosmic microwave background looks almost exactly the same. The temperature, the pattern of fluctuations, the statistical properties, all consistent across the entire sky. This uniformity is both reassuring and puzzling. It's reassuring because it suggests that the laws of physics are the same everywhere, at least within our observable universe. We're not in some special location. The universe looks the same in all directions, which means we're not near an edge or a centre. But it's puzzling because regions of space on opposite sides of the observable universe have never been in contact with each other. They're too far apart. Light hasn't had time to travel between them since the Big Bang. So how did they end up looking so similar? How did they know to have the same temperature and density? This is called the horizon problem, and it's one of the key pieces of evidence for cosmic inflation. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing faster than the speed of light. This isn't a violation of relativity, by the way. Objects can't move through space faster than light, but space itself can expand at any rate. During inflation, regions that were once close together and in thermal equilibrium were stretched apart to distances far larger than the observable universe. That's why everything looks uniform. It all came from the same tiny patch of space before inflation blew it up to cosmic scales. Inflation also helps explain why the universe is so flat. Any initial curvature would have been stretched out by the rapid expansion, like inflating a balloon, until its surface looks perfectly flat on human scales. The observable universe we see today is just a tiny portion of the inflated region, so small that we can't detect any curvature. But here's where inflation makes the question of whether space ends even more complicated. If inflation happened once, it probably happened many times, and might still be happening in regions beyond our observable universe. Different patches of space could have stopped inflating at different times, creating separate bubble universes, each with its own properties. This is called eternal inflation, and it suggests that our observable universe is just one bubble in an eternally inflating multiverse. Space wouldn't end at the edge of our bubble. It would continue into other bubbles, each isolated from the others by regions of space that are still inflating, expanding so fast that nothing can cross between them. This scenario is fascinating and deeply unsettling. It means that the universe as we know it, everything we can see and measure and experience, might be an infinitesimal fraction of reality. Beyond our cosmic horizon, there could be infinite other regions, other bubbles, other domains of existence completely cut off from us. Some might have similar physics to ours. Others might have different values for fundamental constants, making them inhospitable to life or even to matter as we understand it. We would never know. We couldn't know. We're trapped inside our bubble by the finite speed of light and the expansion of space. Let me paint you a picture of just how strange this gets. Imagine you're playing a video game with procedurally generated terrain. As you walk around, the game creates more landscape in front of you. The world is theoretically infinite because the game keeps generating new terrain as long as you keep moving. But you can only see a certain distance ahead because of fog or rendering limits. The land beyond your view doesn't not exist. It just hasn't been generated yet, or you can't see it. The observable universe is like that. Space might continue infinitely beyond what we can see, constantly creating new regions through quantum fluctuations and cosmic expansion. Or it might loop back on itself, or it might just stop at some point we'll never reach. Now let's talk about something that makes all of this even more mind-bending. The expansion of the universe isn't slowing down, it's speeding up. In 1998, astronomers studying distant supernovae made a discovery that shocked the physics community. They expected to find that the expansion of the universe was decelerating, slowed down by the gravitational pull of all the matter it contains. Instead, they found the opposite. The universe is expanding faster now than it was billions of years ago. Something is pushing space apart, accelerating its growth. We call this mysterious force dark energy, but that's really just a placeholder name. We don't know what it is. We don't know where it comes from. We just know that it makes up about 68% of the total energy density of the universe, and it's driving space to expand at an accelerating rate. Dark matter, the invisible stuff that holds galaxies together through gravity, accounts for another 27%. All the normal matter you can see, stars, planets, gas, dust, everything made of atoms, is only about 5% of the universe. We're a tiny minority in a cosmos dominated by things we can't see or understand. This accelerating expansion has profound implications for the question of whether space ends. If the expansion keeps accelerating, galaxies beyond our local group will eventually be carried away from us faster than light can travel. They'll cross our cosmic horizon and disappear from view, not because they're destroyed, but because the space between us is growing so fast that their light can no longer reach us. In a sense, the observable universe will shrink even as space itself grows larger. Billions of years from now, any intelligent beings in our galaxy will look out at the night sky and see almost nothing. The cosmic microwave background will be redshifted beyond detection. Distant galaxies will have vanished. They'll live in what appears to be an empty universe, with no evidence of the Big Bang and no way to know that there are other galaxies beyond their horizon. They'll have a much harder time figuring out cosmology than we do, but it gets worse. If dark energy continues to dominate and the expansion keeps accelerating, we might be headed toward a big rip. As space expands faster and faster, the forces that hold structures together, gravity, electromagnetism, the strong and weak nuclear forces, will eventually be overcome. First, galaxy clusters will be torn apart, then individual galaxies, then star systems, then stars themselves, ripped to shreds by the expansion of space. Eventually planets will be torn apart, then molecules, then atoms, then atomic nuclei, until finally even subatomic particles are shredded by the expansion. Space would effectively end because there would be nothing left to exist in it, just isolated fragments of matter accelerating away from each other faster than light, unable to interact, unable to form structures, unable to do anything but drift alone in an ever-expanding void. That's one possible end for space. Not a boundary in location, but a boundary in time. A moment when the fabric of space itself becomes so stretched and thin that reality as we know it ceases to exist. But we don't know if that will happen. It depends on the nature of dark energy, which we don't understand. Dark energy might be a cosmological constant, a fixed energy density in space that stays the same as the universe expands, or it might change over time, growing stronger or weaker. If it weakens, the universe might stop accelerating and eventually collapse back on itself in a big crunch. If it strengthens, we get the big rip. We simply don't know yet. Let's step back and think about this from a different angle. What would it even mean for space to have an edge? In our everyday experience, edges are places where something ends and something else begins. The edge of a table is where the table stops and the air starts. The edge of a lake is where the water ends and the land begins. But space isn't like that. Space is not in something. It's not embedded in a larger medium. If space has an edge, There's no other side. There's no beyond. There's just not space, which is a concept that breaks language and thought. Some physicists have proposed that the edge of space, if it exists, might be a place where the laws of physics themselves break down, where the equations that describe space-time stop making sense, where quantum mechanics and general relativity, the two pillars of modern physics, both fail simultaneously. This would be similar to what happens at the centre of a black hole, where general relativity predicts a singularity, a point of infinite density and curvature. Singularities are places where our theories give nonsensical answers, infinities where there should be finite numbers. They're not so much real places as they are signs that our understanding is incomplete. The edge of space, if it exists, might be like that, a mathematical artifact indicating that we're asking the wrong questions or using the wrong framework. Perhaps the question itself, does space end, is based on flawed assumptions. Maybe space is not the kind of thing that can end. Maybe it's more like a mathematical structure, existing independently of physical reality in some Platonic sense. Or maybe space is emergent, not fundamental, arising from something deeper that we don't yet understand. In quantum gravity theories, space and time might not be the basic ingredients of reality. They might emerge from more fundamental entities, quantum bits of information or networks of relationships that give rise to space-time at large scales. If space is emergent, then asking where it ends is like asking where the internet ends. The internet isn't a physical object in one location. It's a network, a pattern of connections between computers. It exists wherever the network exists. If you unplug all the computers, the internet doesn't have an edge. It just stops existing. Space could be similar. It might exist wherever there's structure and information to support it. Beyond some limit, if there's no structure and no information, there's simply no space, not an edge, just an absence. This is speculative, of course. We're reaching the limits of what current physics can tell us. But that's where the question of whether space ends ultimately leads, to the boundaries of human knowledge, to places where mathematics and philosophy and physics blur together, where we can ask questions but not yet answer them with certainty. So does space end? The honest answer is we don't know. It might be infinite, stretching on forever in all directions with no boundary. It might be finite but unbounded, curved back on itself so that you could travel forever without reaching an edge. It might have edges in dimensions we can't perceive. It might be one bubble in an infinite multiverse. It might be emergent, not fundamental, existing only where there's structure to support it. Or it might be none of these things. It might be something we haven't imagined yet, something that requires new physics, new mathematics, new ways of thinking about reality itself. What we do know is that the question itself has driven some of the most important discoveries in the history of science. Trying to understand where space ends has led us to general relativity, to quantum mechanics, to the discovery of cosmic expansion, to the realization that the universe had a beginning. Every time we've pushed at the boundaries of this question, we've learnt something profound about reality. And maybe that's the real answer. Maybe space doesn't end because questions never do. Every answer opens up new mysteries. Every discovery reveals how much we still don't understand. The universe is not a puzzle with a final solution. It's an infinite fractal of questions, each one leading to deeper ones, each answer revealing new layers of complexity. Let's explore some of those deeper layers. One of the most profound insights from modern physics is that space and time are not separate things. They're unified into space-time, a four-dimensional structure where the 3 dimensions of space and 1 dimension of time are woven together. This has strange consequences that affect how we think about the end of space. In space-time, events don't just have locations. They have locations in both space and time. Your birth happened at a specific place in a specific moment. Those coordinates in space-time define that event. Now here's the weird part. Different observers moving at different speeds will disagree about the distance between events and the time between events, but they'll agree on the space-time interval, a combination of space and time that remains constant. This is what relativity is all about. Space and time are flexible and observer-dependent, but space-time is absolute. This has implications for cosmic horizons and the end of space. The edge of the observable universe is not just a spatial boundary, it's a boundary in space-time. It marks the region from which light has had time to reach us since the beginning of the universe. But because space and time are linked, asking where space ends is intimately connected to asking when it ends. The Big Bang was both the beginning of space and the beginning of time. If there's an end to space, it might also be an end to time, or a transformation into something where our usual concepts of space and time no longer apply. String theory, one of the leading candidates for a theory of quantum gravity, suggests that space might have more dimensions than we perceive. In most versions of string theory, there are 10 or 11 dimensions total. 3 large spatial dimensions that we move through, 1 time dimension, and 6 or 7 extra spatial dimensions that are compactified, curled up into tiny shapes at every point in space. These extra dimensions are far too small to observe directly. They're smaller than atoms, smaller than protons, smaller than quarks, existing at the Planck scale, about 10 to the minus 35 meters. Why would the universe have extra dimensions? In string theory, fundamental particles are not point-like objects. They're tiny vibrating strings, or in some versions, higher dimensional membranes. The different vibrations of these strings correspond to different particles. An electron is one vibration pattern, a photon is another, a quark is yet another. The strings vibrate in all the dimensions available to them, including the extra compactified ones. The geometry of those extra dimensions determines which particles can exist and what properties they have. Change the shape of the extra dimensions, and you change the physics. If extra dimensions exist, they could provide an answer to the question of where space ends. Our 3 large dimensions might be infinite, but the extra dimensions have boundaries. They're finite structures with specific shapes and sizes. In some models, our entire observable universe could be confined to a 3-dimensional membrane, a brane, floating in a higher dimensional space called the bulk. The other branes might exist nearby in the extra dimensions, close in higher dimensional terms but completely inaccessible to us because we're stuck on our brane. These parallel branes could be entire separate universes with their own space, time and matter, existing just a millimeter away from us but in a direction we can't point to because it's perpendicular to all 3 of our spatial dimensions. Imagine you're a character drawn on a piece of paper. You can move left and right, forward and backward across the surface, but you can't move up off the page because up doesn't exist in your 2-dimensional world. Now imagine there's another piece of paper parallel to yours, just a centimetre above it. Another 2-dimensional universe with its own characters and its own physics. You and those characters are extremely close in the 3rd dimension, but you can never meet because you can't move in that direction. You're confined to your sheet of paper. Brainworld scenarios work the same way. We might be right next to other universes in higher dimensions, but we're trapped in our 3-dimensional brane. This raises a fascinating possibility. What if gravity can leak between branes? Most forces, electromagnetism, the strong and weak nuclear forces, are confined to our brane. But gravity in these models is different. It propagates through all of space-time, including the bulk and the extra dimensions. That's why gravity is so much weaker than the other forces. It's not weak, it's diluted, spreading out through extra dimensions while the other forces are concentrated on our brane. If gravity leaks into the bulk, then other branes could gravitationally affect us. We might detect the presence of parallel universes through subtle gravitational effects, distortions in space-time that don't correspond to any matter we can see. Some physicists have proposed that dark matter, the invisible substance that makes up most of the matter in the universe, could be explained by parallel branes. Perhaps dark matter is just ordinary matter on a nearby brane. It gravitationally affects us because gravity crosses between branes, but we can't see it or touch it because light and other forces don't cross. This is speculative, and there's no direct evidence for it yet, but it's an example of how thinking about extra dimensions and the structure of space can lead to testable predictions. Now let's talk about black holes, because they're intimately connected to the question of whether space ends. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. The boundary of a black hole is called the event horizon. It's not a physical surface, it's just a point of no return. Cross the event horizon, and you're inevitably pulled toward the center, toward the singularity. The singularity is where things get truly strange. According to general relativity, all the mass of the black hole is compressed into a single point of infinite density. The curvature of space-time becomes infinite. Time and space swap roles. Inside the event horizon, the direction toward the singularity is not a direction in space. It's a direction in time. You're not falling through space toward the center. You're moving forward in time toward the moment when you reach the singularity. It's as inevitable as tomorrow. But here's the thing. Singularities are probably not real. They're almost certainly artifacts of our incomplete understanding. When a theory predicts infinities, it's usually a sign that the theory has reached its limits. General relativity describes black holes beautifully at large scales, but it breaks down at the singularity. Quantum mechanics should be important there, but we don't have a complete theory of quantum gravity to describe what really happens. The singularity might be replaced by something else, perhaps a region of highly curved but finite space-time, or a bridge to another region of space, or even another universe. Some solutions to Einstein's equations, mathematical curiosities that might not exist in nature, describe black holes that don't have singularities. Instead, they have wormholes, tunnels through space-time that connect two different regions. You could enter a black hole, travel through the wormhole and emerge from a white hole in another part of the universe, or even in a different universe entirely. These are called Einstein-Rosen bridges, and while they're mathematically possible, they're almost certainly not stable. They would collapse before anything could pass through them, but they hint at a deeper structure to space-time, a network of connections that could link distant regions or separate universes. Black holes also raise questions about information and the end of space. When something falls into a black hole, it seems to disappear from the universe. Its information, everything that defined it, is lost behind the event horizon. But quantum mechanics says that information can't be destroyed. This creates a paradox. What happens to the information? Stephen Hawking showed that black holes aren't completely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Over immense timescales, this radiation causes black holes to evaporate, eventually disappearing completely. But Hawking radiation appears to be random, carrying no information about what fell in. So when the black hole evaporates, where does the information go? This is the black hole information paradox, and it's one of the deepest problems in theoretical physics. Various solutions have been proposed. Maybe information is encoded in the Hawking radiation in subtle ways we don't yet understand. Maybe it's stored on the event horizon, which acts like a holographic screen recording everything that falls in. Maybe information escapes through wormholes or leaks into other dimensions. Or maybe our understanding of space-time itself needs to change. Some physicists think the paradox is telling us that space is not fundamental, that it emerges from quantum entanglement, connections between particles that link them across space. If space is emergent from entanglement, then the question of whether it ends becomes a question about the structure of entanglement in the universe. Space would exist wherever particles are entangled. It would have properties that depend on the pattern of entanglement, and it could potentially end or change at boundaries where entanglement networks connect to other networks or simply stop. This leads us to one of the most radical ideas in modern physics, the idea that the universe might be a hologram, not a literal hologram like the ones on credit cards, but something deeper and stranger. The holographic principle proposed by physicists studying black holes, suggest that all the information contained in a volume of space can be encoded on the boundary of that volume. A three-dimensional region can be completely described by a two-dimensional surface surrounding it. This sounds insane, but there's good reason to take it seriously. Black holes have entropy, a measure of how much information they contain. You might expect that entropy to be proportional to the volume of the black hole. Bigger black hole, more space for information. But it's not. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This suggests that the information content of a black hole is stored on its surface, not in its interior. And if that's true for black holes, maybe it's true for all of space-time. The holographic principle has been made more concrete in theories like AD-CFT correspondence, a mathematical relationship between a theory of gravity in a certain type of curved space and a quantum field theory without gravity on the boundary of that space. It's like how a hologram works. A two-dimensional pattern on film contains all the information needed to reconstruct a three-dimensional image. In AD-CFT, a quantum theory on the boundary contains all the information about gravity and space-time in the interior. The three-dimensional space we experience might be a kind of projection from information stored on a distant two-dimensional surface. If this is correct, and it's supported by extensive mathematical evidence though not yet proven experimentally, then space is not fundamental, it's emergent. It arises from patterns of information and entanglement, and that changes everything about the question of whether space ends. Space would end wherever the holographic encoding ends. It would be finite in the sense that there's only so much information that can be stored, but the boundary would not be a place you could travel to. It would be a mathematical structure, a surface in an abstract space, not a physical location. These ideas are at the cutting edge of theoretical physics, and they're highly speculative, but they represent the direction the field is moving, away from thinking of space as a fixed stage and toward thinking of it as an emergent phenomenon arising from deeper quantum structures. This is a profound shift in perspective, as radical as Einstein's replacement of Newton's absolute space with curved space-time. Now, let's consider what all of this means for the multiverse. The idea that our universe might be one of many is not new, but modern physics has given it several concrete forms. There's the bubble universe multiverse from eternal inflation, where different regions of space stop inflating at different times, creating separate universes with different properties. There's the quantum multiverse from the many worlds interpretation of quantum mechanics, where every quantum measurement creates a branching of reality into separate universes for each possible outcome. There's the brain multiverse from string theory, where multiple brains exist in a higher dimensional bulk. And there's the mathematical multiverse, the idea that every mathematically consistent structure exists as a physical reality somewhere. These multiverse scenarios offer different answers to whether space ends. In the bubble multiverse, each bubble has its own space that might be infinite or finite. The spaces of different bubbles are separate, divided by regions of eternally inflating space. You could say that space ends at the boundary of each bubble, but new space is constantly being created by inflation. In the quantum multiverse, each branch has its own complete copy of space. There's no boundary between branches because they don't exist in the same space-time. They're separate realities that diverged from a common history. In the brain multiverse, our three-dimensional space exists on a brain, and it might be infinite, but there are other spaces on other brains. Space doesn't end. It extends in directions we can't access. And in the mathematical multiverse, every possible space exists somewhere. So the question of whether space ends is replaced by the question of which spaces are mathematically possible. The multiverse is controversial. Some physicists embrace it as a natural consequence of well-established theories. Others reject it as untestable speculation. The core problem is that if other universes are truly separate from ours, beyond our cosmic horizon or in different branches or on different brains, then we can't observe them. We can't test predictions about them. They might as well not exist from a scientific standpoint. But proponents argue that the multiverse makes testable predictions. The properties of our universe, the values of fundamental constants like the strength of gravity or the mass of the electron might be explained by selection effects. If there are many universes with different constants, we naturally find ourselves in one where the constants allow for life. This is called the anthropic principle, and it's deeply divisive. Some see it as a legitimate scientific explanation. Others see it as giving up on finding deeper reasons for why the universe is the way it is. Regardless of where you stand on the multiverse, it represents an attempt to answer the question of whether space ends by expanding the concept of space itself. Maybe space doesn't end because it's part of a larger structure, a multiverse where different spaces coexist. Maybe our universe is just one room in an infinite mansion, and asking whether space ends is like asking whether rooms end. Yes, each room has walls, but there are more rooms beyond. Let's return to something more observational. What can we actually measure about the structure and extent of space? We've talked about the cosmic microwave background and what it tells us about the shape of the universe. We've talked about the accelerating expansion driven by dark energy. But there are other observations that constrain our understanding of whether space ends. One important measurement is the distribution of galaxies in the universe. By mapping millions of galaxies and measuring their distances, astronomers have created three-dimensional maps of the cosmic web, the large-scale structure of the universe. These maps show filaments and voids, regions where galaxies cluster together and regions that are mostly empty. The pattern is remarkably uniform at the largest scales. No matter which direction you look, the distribution of galaxies looks statistically the same. This is called cosmic isotropy, and it's strong evidence that we're not in a special location. The universe looks the same in all directions, which suggests it doesn't have an edge that we're near. Combined with the cosmological principle, the assumption that the universe is homogeneous and isotropic, this means that if the universe has an edge or boundary, it's far beyond what we can observe. Otherwise, we'd see asymmetries. Galaxies would be more densely packed in one direction than another. The cosmic microwave background would be hotter or colder depending on which way we looked. We don't see that. The universe is remarkably uniform, suggesting that if it has edges, they're far beyond our horizon. Another key observation is the measurement of cosmic expansion using supernovae and other distance indicators. Type 1a supernovae are exploding stars that reach a predictable peak brightness. By measuring how bright they appear from Earth and comparing that to how bright they actually are, astronomers can calculate their distance. By measuring the redshift of the light from the galaxies hosting these supernovae, they can determine how fast those galaxies are moving away from us. Plotting distance versus velocity gives us the expansion history of the universe, and what we see is that the expansion is accelerating. Distant galaxies are moving away faster than they should be if the expansion was slowing down under gravity. This accelerating expansion has profound implications. It means that the observable universe will shrink in the future as more and more galaxies cross our cosmic horizon and disappear from view. It means that intelligent beings in the far future will have a much harder time figuring out cosmology because they won't have access to the evidence we have today. And it means that the ultimate fate of the universe depends on the nature of dark energy. If dark energy remains constant, the universe will expand forever, cooling and diluting until it reaches a state of maximum entropy called heat death. Stars will burn out, black holes will evaporate, and eventually nothing will remain but a cold, diffuse sea of particles that can no longer interact in meaningful ways. Space won't end, but it will become so vast and empty that the concept of space almost loses meaning. If dark energy grows stronger over time, we get the Big Rip scenario. The expansion accelerates so much that it overcomes all forces holding structures together. First, galaxy clusters are torn apart, then galaxies, then solar systems, then stars and planets, eventually atoms and subatomic particles. The fabric of space itself is stretched so violently that matter can no longer exist. This would be an end to space in the sense that space would destroy everything within it. The structure that gives space meaning would be gone. If dark energy weakens or reverses, the universe could stop expanding and begin contracting, leading to a big crunch. All of space would collapse back to a singularity, potentially giving rise to a new Big Bang in a cyclic universe. In this scenario, space doesn't end. It transforms, cycling through phases of expansion and contraction eternally. Or at least until quantum gravity effects take over and do something we can't predict. We don't know which of these scenarios will play out because we don't understand dark energy. It's the biggest mystery in cosmology. We know it exists because we see its effects, but we don't know what it is. It could be a property of space itself, vacuum energy from quantum fields. It could be a new field permeating the universe. It could be a sign that our theory of gravity needs modification at cosmic scales. We're collecting more data, building better telescopes, mapping the universe in ever greater detail. But for now, the nature of dark energy and the ultimate fate of space remain unknown. Let's think about what it would be like to approach an edge of space if one existed. Imagine you're in a spaceship travelling through the universe. You've been going for billions of years, somehow staying alive through technology we can't imagine. You've crossed the entire observable universe and kept going. Galaxies thin out. Space becomes darker and emptier. You're in a void between cosmic filaments, a region with almost no matter. But you keep going. Eventually, you approach some kind of boundary. What would that be like? If space simply ends, you'd reach a point where you can't go farther. Not because there's a wall, but because there's no more space to move into. The concept of forward ceases to have meaning. Your instruments would show that distance becomes undefined. Perhaps the geometry of space-time would become increasingly distorted as you approach the edge, with time dilation effects becoming extreme. You'd experience time differently than someone far from the edge. Perhaps time itself would stop at the boundary, and you'd be frozen at the moment of reaching it, unable to proceed or turn back. Or maybe the edge is not a sharp boundary but a gradual transition. Space could become increasingly curved or compactified as you approach the edge, so that distances become shorter and shorter, until moving forward doesn't take you anywhere new. You'd be like an ant walking toward the North Pole. The closer you get, the less distance is left to cover, until finally you reach a point where north no longer exists as a direction. Every direction from the North Pole is south. Every direction from the edge of space, if it's like that, might be back toward the interior. Another possibility is that the edge is not a location but a conceptual boundary. Perhaps space is infinite, but the laws of physics change beyond a certain point. You cross a threshold where the constants of nature take different values. Electromagnetism becomes stronger or weaker. The mass of electrons changes. Chemistry as you know it stops working. Matter dissolves into forms you can't recognize. You wouldn't hit a wall. You'd gradually enter a region where reality operates by different rules, where the space itself has different properties. Or perhaps there is no edge because space loops back on itself. You travel in what seems like a straight line for long enough, and you end up back where you started. This is hard to visualize in 3 dimensions, but it's mathematically consistent. Just as an ant walking in a straight line on a sphere eventually returns to its starting point, you could travel through a curved universe and come back to where you began. The universe would be finite with a specific volume, but it would have no edge because there's no point you can't move beyond. These scenarios are speculative, but they illustrate how strange the answer to whether space ends could be. Our intuitions, shaped by living in a bounded world with edges everywhere, don't prepare us for the cosmic scale. The universe doesn't owe us intuitive answers. It operates according to principles that often defy common sense. One more thing to consider is the role of consciousness and observation in defining space. In quantum mechanics, observation plays a crucial role in determining the state of a system. Before you measure a particle's position, it doesn't have a definite position. It exists in a superposition of all possible positions. The act of measurement collapses the wave function and forces the particle to be in one place. This has led some physicists to wonder whether consciousness plays a role in creating reality. Most physicists reject this idea, arguing that decoherence and interaction with the environment, not conscious observation, cause wave function collapse. But a few take it seriously. If consciousness is necessary to collapse wave functions and create definite outcomes, then reality as we experience it might depend on observers. Space might only exist in the form we know it because there are conscious beings to observe it. In regions of the universe with no observers, space might exist in some different form, or might not be fully defined. This is highly speculative and controversial, but it raises a fascinating question. If space depends on observation, what happens at the edge of the observable universe? Does space exist beyond that boundary in the same way it exists here, or does it take some less defined form? Is the act of observation by intelligent beings what brings space into full existence? These are questions at the intersection of physics, philosophy, and consciousness studies, and we're nowhere near answering them, but they illustrate just how deep the question of whether space ends can go. Eleanor Zez, KBF 37,500 character, Folitatum Avejage. As we near the end of our journey, let's pull back and look at the big picture. We started with a simple question: where does space stop? And we've discovered that the answer is anything but simple. Space might be infinite, extending forever in all directions. It might be finite but unbounded, curved back on itself like the surface of a sphere. It might have edges and extra dimensions we can't perceive. It might be one of many spaces in a multiverse. It might be emergent, not fundamental, arising from deeper quantum structures. It might not end because it's constantly being created by cosmic inflation. Or it might end in time rather than space, destroyed in a big rip or collapsing in a big crunch. The honest truth is that we don't know, and we may never know with complete certainty. Science has limits, not because scientists aren't clever enough, but because there are fundamental constraints on what we can observe and measure. We're trapped inside our cosmic horizon, able to see only the portion of the universe from which light has had time to reach us. Everything beyond that is inaccessible, possibly forever. We can theorize, we can build models, we can make predictions, but we can't directly observe regions of space beyond our observable universe. That doesn't mean the question is pointless. Far from it. Asking where space ends has driven some of the most profound discoveries in physics. It led to general relativity, to the realization that space is curved and dynamic. It led to the discovery of cosmic expansion, to the Big Bang theory, to our understanding that the universe had a beginning. It led to inflation theory, to ideas about the multiverse, to the holographic principle and theories of quantum gravity. Every time we push at this question, we learn something new about the nature of reality. And maybe that's the real answer. Space doesn't end because inquiry never does. Every answer reveals new questions. Every discovery shows us how much we still don't understand. The universe is not a puzzle with a final piece that completes the picture. It's an infinite fractal of mysteries, each one opening onto deeper layers of complexity. You're a part of this universe, made of atoms forged in the cores of dying stars, assembled through billions of years of cosmic evolution into a conscious being capable of asking these questions. You can stand on a small rocky planet orbiting an ordinary star and contemplate the nature of space itself, wondering whether it ends, how it began, what lies beyond the cosmic horizon. That ability, that capacity for wonder and inquiry, is perhaps the most remarkable thing in the known universe. So the next time you look up at the night sky, remember that you're not just looking at stars, you're looking at the fabric of space-time itself, stretched across distances so vast that light takes billions of years to cross them. You're seeing the universe as it was in the past, light from distant galaxies showing you what they looked like millions or billions of years ago. You're part of a cosmos that might be infinite or might curve back on itself, that might be one of many or all there is, that had a beginning and might have an end or might go on forever, and you don't know. None of us do. But we keep asking, keep observing, keep thinking, keep building better theories and better instruments. We push at the boundaries of knowledge, trying to understand where space stops, if it stops at all. That quest, that drive to comprehend the universe we find ourselves in, is what makes us human. It's what makes this fleeting moment of consciousness in a vast and ancient cosmos meaningful. Space might not end, but this exploration does, for now. Until someone asks the question again, approaches it from a new angle, discovers something unexpected that changes everything we thought we knew. That's how science works. That's how understanding grows. One question at a time, one discovery at a time, pushing ever outward toward the edges of knowledge, even if the edges of space itself remain forever beyond our reach. Let's dive even deeper into the cosmic mystery. We've explored the physics, the mathematics, the observational evidence. But there's another dimension to the question of whether space ends, one that's equally important. The philosophical dimension. What does it mean for space to exist? What does it mean for something to end? These aren't just abstract questions. They cut to the heart of how we understand reality itself. Consider this. When you say space ends, you're implicitly assuming that space is a thing that can have boundaries. But what if that assumption is wrong? What if space is more like a relationship between objects than a container they exist in? In this relational view, which goes back to the philosopher Leibniz, space doesn't exist independently. It's just a way of describing how things are positioned relative to each other. If you removed all the matter and energy from the universe, there would be no space left because there would be nothing to have spatial relationships. Space would simply cease to exist, not because it ended at some boundary, but because there would be no relationships left to constitute it. This view is radically different from the Newtonian picture of absolute space, an unchanging stage that exists independently of what's on it. And it's different from the Einsteinian picture too, though closer in some ways. In general relativity, space-time is a physical thing that exists even in the absence of matter, though matter and energy affect its shape. In the relational view, space-time is emergent, arising from the pattern of relationships between fundamental entities. If there are no entities, there's no space-time. Modern physics is actually moving towards something like the relational view. In quantum gravity theories, particularly those based on loop quantum gravity or causal set theory, space-time is not fundamental. It emerges from a network of quantum relationships. At the smallest scales, the Planck scale, space-time as we know it breaks down into something more discrete, more quantum, more abstract. Space becomes granular, made of tiny chunks of volume that can't be subdivided further. These chunks are connected in networks, and the properties of space-time emerge from the structure of those networks. If this is correct, then asking where space ends is like asking where a chess game ends. A chess game doesn't end at a spatial boundary. It ends when the rules and relationships that define it no longer apply. When the game is over, when the pieces are put away, the game doesn't exist anymore. Not because it reached an edge, but because the structure that constituted it has dissolved. Space might work the same way. It exists where there are quantum relationships to support it. Beyond some boundary, if quantum relationships change or cease, space simply stops being defined. There's no edge to cross because there's nothing on the other side. There's just the absence of the relationships that create space. This brings us to another deep question. What is nothingness? When we talk about what might be beyond space, we often say nothing. But what does that mean? Absolute nothingness is harder to define than you might think. Is it the absence of matter, the absence of energy, the absence of fields, the absence of space-time itself, the absence of physical laws, the absence of mathematical structure? Each of these is a different kind of nothing, and they have different implications. In everyday language, nothing usually means the absence of stuff. An empty room has nothing in it, meaning no furniture, no people, no objects. But the room still has air, light, electromagnetic fields, gravitational fields. It still has space and time. It's not truly nothing. In physics, a vacuum is often called nothing, but as we've discussed, quantum vacuums are full of activity. Virtual particles pop in and out of existence. Quantum fields fluctuate. There's vacuum energy. A quantum vacuum is not nothing. It's a very specific state of something. True nothingness would have to be the absence of everything. No matter, no energy, no fields, no space-time, no physical laws, no possibility of anything happening. This is sometimes called metaphysical nothingness, and it's unclear whether such a state is even coherent. Can you have literally nothing and have it be stable? Or would quantum fluctuations inevitably arise from nothing creating something? Some physicists have argued that absolute nothingness is unstable, that quantum mechanics allows for the spontaneous creation of universes from nothing. This is a controversial idea, and it depends on what you mean by nothing. If quantum mechanics applies, then you already have something, the laws and structure of quantum mechanics. That's not nothing. Philosopher David Albert has pointed out that when physicists talk about creating something from nothing, they usually mean creating particles from a vacuum state, but the vacuum state is not nothing. It's a state with properties, described by quantum field theory. It has energy, it has structure. Calling it nothing is misleading. Real nothingness, if it exists, would have no properties, no structure, no laws, and from that it's hard to see how anything could arise. The universe might require a why, a reason for existing rather than not existing, and physics alone might not be able to answer that question. This has led some physicists and philosophers to propose that existence itself is necessary, that something must exist because pure nothingness is logically impossible or unstable. If there's any possibility of something existing, then in the space of all possible states something will exist. This touches on the anthropic principle again. We find ourselves in a universe that exists because non-existence doesn't allow for observers to ask why. It's a tautology, but it might be the closest we can get to an answer. Now let's consider time again, because time and space are so deeply connected that we can't fully understand one without the other. If space ends, does time end too? At the Big Bang, both space and time began together. Before the Big Bang, there was no before because time didn't exist. You can't have temporal relationships without time, and you can't have time without change, without a sequence of events. If the universe started from a singularity, a state of infinite density and temperature, then time started when that singularity began to expand. There's no meaningful sense in which time existed before that moment. This is profoundly counterintuitive. We're used to thinking of time as an infinite line stretching into the past and future. The idea that time has a beginning feels wrong, like there must have been something before. But before is a time concept. Asking what happened before time began is like asking what's north of the North Pole. The question contains a conceptual error. North is defined relative to a coordinate system that has a pole. Beyond the pole, north doesn't point anywhere. Similarly, before is defined relative to a time coordinate that begins at the Big Bang. Before the Big Bang, before doesn't point anywhere. Some cosmological models do allow for time before the Big Bang. In cyclic models, the universe goes through repeated cycles of expansion and contraction. The Big Bang is not the beginning of time, but the beginning of this cycle. Before it, there was a previous cycle, and before that another, potentially infinitely far back. In these models, time is eternal, but space is periodically created and destroyed. In eternal inflation models, our Big Bang was a local event in an eternally inflating multiverse. Time extends infinitely into the past in the inflating space, though each bubble universe has its own local beginning of time. And then there are models where time is emergent, not fundamental. In some approaches to quantum gravity, time arises from something more, basic perhaps from the quantum entanglement structure of the universe. At the most fundamental level, there might be no time, just a timeless quantum state. Time would emerge when you consider subsystems of the universe and how they evolve relative to each other. This is called the problem of time in quantum gravity, and it's one of the hardest unsolved problems in physics. If time is emergent, then asking when time began or ends is a question that only makes sense at the emergent level, not at the fundamental level. The end of time is equally strange to think about. In the heat-death scenario, the universe expands forever, cooling and diluting until it reaches thermodynamic equilibrium. In this state, there's maximum entropy. No energy gradients remain to drive processes. Stars have all burned out. Black holes have all evaporated. All matter has decayed into radiation and scattered across infinite space. Does time still exist in this state? Technically, yes, in the sense that you could still define a time coordinate, but nothing changes. There are no events, no processes, no way to measure time's passage. It's a state of eternal changelessness. Time exists, but it's meaningless because nothing happens. In the Big Rip scenario, time ends in a different way. The accelerating expansion of space becomes so extreme that it tears apart all structures down to subatomic particles. At some finite time in the future, the universe reaches a moment where space itself becomes infinitely stretched. Curvature becomes infinite, and the laws of physics break down. This is a future singularity, similar in some ways to the singularities inside black holes. Beyond that moment, time might not be defined, or it might continue in some form we can't predict, because our theories fail at singularities. In the Big Crunch, time might end when the universe collapses back to a singularity. All of space and time would contract to a single point. Or, as in cyclic models, time might continue through the singularity into a new cycle. The singularity would be a moment of maximum density and temperature, but not the end of time, just a transition point. These scenarios show that the end of space and the end of time are intimately connected. You can't have one without considering the other. If space ends at some boundary, time might behave strangely near that boundary. If time ends at some moment, space might cease to exist at that moment. Space-time is a unified structure, and its beginning and end, if they exist, are properties of that unified structure. Let's shift perspective again and think about what advanced civilizations might know about whether space ends. We're a young species, barely out of the cradle of our home planet. Our technology is primitive. Our understanding of physics is incomplete. But imagine a civilization a billion years more advanced than us. What might they know? What might they be able to measure? An advanced civilization might be able to send probes across intergalactic distances, mapping the universe far beyond our observable horizon. They might have instruments sensitive enough to detect the subtle patterns in the cosmic microwave background that could reveal large-scale curvature or connections to other universe regions. They might understand dark energy and dark matter, solving mysteries that we're just beginning to grapple with. They might have a complete theory of quantum gravity, allowing them to understand what happens at singularities and at the smallest scales of space-time. With that knowledge, they might be able to answer definitively whether space is infinite or finite, whether it has boundaries or curves back on itself. They might even be able to detect other universes in a multiverse, if such things exist, through gravitational effects or other subtle signals. They might understand the fundamental nature of space-time, whether it's emergent or fundamental, continuous or discrete. All the questions we're struggling with might be answered for them, but even they might face limits. Even a civilization with godlike technology and understanding might not be able to observe beyond certain horizons. If the universe is truly infinite, they can't observe all of it. If there are other universes completely causally disconnected from ours, they can't detect them. If there are phenomena that require energies beyond what's possible in our universe, they can't access them. There might be questions about the nature of space that are fundamentally unanswerable, not because we're not clever enough, but because the structure of reality itself limits what can be known. This is a humbling thought. We like to think that given enough time and resources, we can figure anything out. But there might be truths about the universe that are forever beyond the reach of any observer within it. These would be true but unknowable facts, things that are real but can't be measured or verified from our position in space-time. The question of whether space truly ends might be one of them, yet we keep trying. That's what science is, the systematic attempt to understand reality through observation, experimentation, and theory. We build bigger telescopes. We design more sophisticated experiments. We develop new mathematical frameworks. Each generation pushes a little further, understands a little more. Even if we never reach final answers, the journey itself is worthwhile. Every discovery, every insight, every new question adds to the tapestry of human knowledge. And there's something profound about this quest. It connects us to every human who ever looked up at the night sky and wondered. Ancient astronomers tracking the motions of planets, medieval scholars debating the nature of the cosmos, Galileo turning his telescope toward Jupiter's moons, Einstein scribbling equations that revealed the curvature of space-time, Hubble discovering that the universe is expanding. Every person who contributed to our understanding of space and time is part of a continuous thread, a conversation that spans centuries and will continue for centuries more. You're part of that thread too. When you ask where space ends, you're participating in humanity's oldest and deepest inquiry. You're exercising the same curiosity that drove our ancestors to map the stars, to build monuments aligned with celestial events, to develop mathematics and physics and cosmology. That curiosity is part of what makes us human. It's what drove us down from the trees, across the savannas, over the oceans, and eventually into space. It's what will drive us further still, perhaps to other stars, perhaps to understand the deepest nature of reality itself. Now let's explore one more aspect of this question, one that ties together physics, philosophy, and perhaps even consciousness. What does it mean for something to exist? Space, if it exists, is not the kind of thing you can touch or see directly. You can't pick up a piece of space and examine it. You infer its existence from the behavior of things in it. Objects move, light travels, forces propagate. All of these phenomena suggest that there's a structure, a framework in which they occur. We call that framework space. But what if space is not a thing that exists independently? What if it's more like a concept, a useful abstraction we use to organize our observations? In this view, when we ask whether space ends, we're really asking whether our conceptual framework for organizing observations has limits. And the answer might be that it does. At extremely small scales, quantum foam and uncertainty might make the concept of space break down. At extremely large scales, cosmic horizons and disconnected regions might mean that space as a unified whole doesn't exist. We can talk about the space we can observe, the space we can interact with, but a concept of all of space might not be well defined. This isn't as radical as it sounds. We already know that many concepts we use have limited domains of applicability. Temperature is a useful concept for systems with many particles, but it doesn't apply to individual atoms. Solidity is a useful concept at human scales, but at atomic scales, matter is mostly empty space with tiny particles held together by forces. Up and down are useful concepts on Earth's surface, but they lose meaning in space where there's no preferred direction. Space itself might be a useful concept at the scales we typically deal with, but it might break down or need replacement at scales far beyond our experience. If space is not fundamental, if it emerges from something deeper, then the question of whether it ends transforms into a question about the underlying structure. Does the quantum foam extend infinitely? Does the network of quantum relationships that gives rise to space-time have boundaries? These are different questions than whether space ends, and they might have different answers. The emergent space could be finite, even if the underlying structure is infinite or vice versa. This brings us to the edge of what current physics can tell us. We're speculating now, exploring ideas that are at the frontiers of research. ideas that might be proven right or wrong in the coming decades as new experiments are performed and new theories developed. But speculation is important. It's how science advances. Someone proposes a wild idea, someone else figures out how to test it, and gradually we narrow down the possibilities, eliminating what doesn't work and refining what does. The question of whether space ends has driven this process for centuries. It will continue to drive it for centuries more. And even if we never get a final answer, even if the question turns out to be more subtle than we thought, asking it pushes us to understand the universe better. It forces us to confront our assumptions, to test our theories, to build better instruments and develop better mathematics. The question itself is valuable, regardless of whether it has a definitive answer. So let's bring this all together. Does space end? Here's what we know. Space is not empty void, but a physical structure that can bend, stretch, and ripple. It's intimately connected to time in a four-dimensional fabric called space-time. The observable universe has a horizon beyond which we can't see, but that horizon is not an edge of space itself. It's just the limit of what light has had time to reach us from since the Big Bang. Beyond our horizon, space almost certainly continues, though we can't observe it directly. Space might be infinite, extending forever in all directions. This is consistent with observations that show the universe is flat or very close to flat. An infinite universe has no edges, no boundaries, no center. It just goes on forever, filled with galaxies and stars and planets, repeating patterns at larger and larger scales. In an infinite universe, everything that can happen does happen somewhere. There are other regions exactly like ours, with copies of you reading these words. There are regions completely different, with alien life forms we can't imagine. Infinity is a strange concept to grapple with, but it might be the reality we live in. Alternatively, space might be finite but unbounded, curved back on itself like the surface of a sphere. A finite universe would have a specific volume, a finite number of galaxies, a finite amount of matter and energy. But it would have no edges. You could travel in a straight line forever and never reach a boundary. Eventually, after crossing the entire universe, you'd return to your starting point from the opposite direction. This is harder to visualize in 3 dimensions, but it's mathematically consistent and possible. Space might have edges in dimensions we can't perceive. If extra dimensions exist, as suggested by string theory and other frameworks, our 3-dimensional space might be embedded in a higher dimensional structure. In that case, space could be finite in some directions and infinite in others, or it could connect to other spaces, other brains, other universes existing in parallel. Space might be one of many in a multiverse. Different regions might have stopped inflating at different times, creating separate bubble universes with different physical properties. Or every quantum measurement might create branching universes for each possible outcome. Or parallel brains might exist in higher dimensions. In any multiverse scenario, the question of whether space ends becomes a question of whether the multiverse as a whole has boundaries, which is even harder to answer than the question about our universe alone. Space might be emergent rather than fundamental. At the deepest level, reality might consist of quantum information, or networks of relationships, or mathematical structures that give rise to space-time at larger scales. In that case, space ends wherever the underlying structure ends or changes, but the underlying structure might be infinite even if the emergent space is finite, or vice versa. And finally, space might end in time rather than location. The universe had a beginning about 13.8 billion years ago. It might have an end in the far future, either through heat death, Big Rip, or Big Crunch. These would be endings of space not at a boundary, but at a moment when space ceases to exist or transforms into something else. We don't know which of these scenarios is correct. We might never know with absolute certainty. But we're gathering more data every year. We're building more powerful telescopes to observe the early universe and distant galaxies. We're conducting experiments to understand dark matter and dark energy. We're developing better theories of quantum gravity. Each piece of evidence narrows down the possibilities, bringing us closer to understanding the true nature of space. What we do know is that the universe is far stranger and more wonderful than our ancestors could have imagined. Space is not a simple container, but a dynamic, structured, quantum mechanical fabric that's intimately connected to time, energy, and matter. The scale of the cosmos is almost beyond comprehension, with distances measured in billions of light years and timeframes measured in billions of years. And yet, despite being tiny creatures on a tiny planet in a vast universe, we've managed to understand much of it. We've measured the age of the universe, mapped its large-scale structure, discovered its expansion, and probed its fundamental laws. That's an extraordinary achievement. It speaks to the power of human curiosity and intelligence. We might not be at the center of the universe. We might be insignificant on cosmic scales, but we're capable of understanding the cosmos we find ourselves in. We can look out at the stars and comprehend what we're seeing. We can ask whether space ends and develop sophisticated theories to address that question. We can build instruments that detect gravitational waves from colliding black holes billions of light years away. We can peer back in time to see the universe as it was when it was only a few 100,000 years old. These capabilities make us remarkable. In all the universe, as far as we know, we're one of the only places where matter has organized itself into complex structures capable of thought and understanding. We're the universe becoming conscious of itself, looking back at its own history, contemplating its own nature. That's profound. That's meaningful. Even if we're alone in the universe, even if there's no other intelligent life anywhere, the fact that we exist and can ask these questions gives the universe a kind of purpose. So when you look up at the night sky and wonder where space ends, remember that you're participating in something ancient and important. You're asking a question that has no easy answer, but demands to be asked anyway. You're exercising a capacity that makes you uniquely human, the ability to wonder about things far beyond your immediate experience. You're connecting to the long tradition of astronomers and physicists and philosophers who came before you, and you're contributing to the ongoing quest to understand reality. Space might not end, or it might end in ways we haven't imagined yet, but the quest to understand it never ends. With every generation, we learn more, we see further, we understand deeper, and even if we never get a final answer, the journey itself enriches us. It expands our minds, challenges our assumptions, and reminds us that we're part of something much larger than ourselves. The universe is vast. Space might go on forever, filled with wonders we'll never see and mysteries we'll never solve. But we're here, we're conscious, and we're asking questions. That's enough. That's more than enough. That's everything. In the end, perhaps the most profound answer to whether space ends is this: we don't know, but we're not afraid to ask. We're not content with ignorance. We're driven to understand, to explore, to push at the boundaries of knowledge even when those boundaries seem impossibly far away. That drive, that curiosity, that refusal to accept easy answers is what makes us human. It's what makes us remarkable. It's what gives our brief existence in this vast cosmos meaning and purpose. So keep asking, keep wondering, keep looking up at the stars and imagining what might be out there, beyond our horizon, beyond our understanding, beyond even our ability to imagine. Keep pushing at the question of where space ends, knowing that the answer, whatever it turns out to be, will be stranger and more beautiful than anything we currently conceive. That's the nature of the universe. It always surprises us. It always exceeds our expectations, and it always rewards those brave enough to ask the biggest questions. The cosmos is not just a place. It's a story, an ongoing narrative of matter and energy, and space and time evolving over billions of years. You're part of that story. Your atoms were forged in stellar furnaces. Your existence is the result of 13.8 billion years of cosmic evolution. And your ability to ask where space ends, to contemplate infinity and boundaries and the nature of reality itself, is the universe's way of understanding itself. That's the real answer to where space ends. It doesn't end because the story doesn't end. The universe keeps unfolding, keeps revealing new mysteries, keeps inspiring new questions. And as long as there are conscious beings to ask those questions, to marvel at the stars, to wonder about the nature of existence, space will continue to be what it's always been. An invitation to explore, to understand, to reach beyond ourselves and touch something infinite. Welcome to the cosmos. It's stranger than you think. It's more beautiful than you imagine. And it's yours to explore, one question at a time, one discovery at a time, one moment of wonder at a time. Where does space end? Maybe nowhere. Maybe everywhere. Maybe the question itself is the answer. A reminder that the universe is endlessly fascinating, endlessly mysterious, and endlessly worthy of our attention and our awe. So go ahead, look up, wonder, ask, explore. That's what the universe wants from you. That's what makes this whole, vast, ancient, incomprehensible cosmos worth being part of. You're here, you're conscious, you're curious, and somewhere out there, beyond the stars, beyond the galaxies, beyond the edge of everything we can see, space might just go on forever, waiting for the next question, the next discovery, the next moment when a conscious being looks up and asks, where does it all end? And the universe, in its infinite wisdom and infinite mystery, whispers back, keep looking, keep asking, keep wondering. Because that's how you find meaning in the void. That's how you light up the darkness. That's how you transform empty space into something filled with purpose and understanding and awe. The journey never ends, and that's exactly how it should be.